Hello, once again, class. We are ready to take up section 11-3, and I think I'm going to go ahead and throw in 11-4 as well. We are going to be doing something that actually you're pretty familiar with. It's just going to look a little different than what maybe you're accustomed to seeing, but I think you know this stuff already. How to simplify rational expressions is really what we're talking about. Simplification of rational expressions. Remember, when we're simplifying rational expressions, we cannot divide by, what's the answer? Cannot divide by 0. That's right. You got it. So what we're going to be doing today is to start with something very, very simple, simplification of fractions. We're going to look at a basic fraction, such as 9/16, and then we're going to ask ourselves, how do we simplify that? Something that I think you're familiar with, or maybe something like 9/12. How do you simplify that? Well, I think you know the answer to these questions, but I think it bears review so that you utilize the same principles for simplification of rational expressions, not just basic fractions with numbers, but fractions that involve variables. And we will use the same approach. Factor, cancel out common factors, and then we have a simplified expression. And again, remember, no radicals in the denominator. You don't leave a square root sign in the denominator or any other root sign if it's going to be in simplified form. Well, I think that pretty much sums it up for the intro. Let's jump on over and start with some simple examples. So off we go to our whiteboard. And here we are. Here is a rational expression, 8/x² minus 16. I would hope that as soon as you look at this, you recognize that the denominator has a special form. You recognize the form of the denominator. Anybody recognize that form? X² minus 16 is the difference of two squares. You got it, the difference of two squares. So what we would want to do then is to factor the denominator initially and then ask ourselves, what are the excluded values? What's another word for excluded values? Another way to describe them, it would be values that create 0 in the denominator. So what we're actually looking for is a factored form of that denominator. So we put x plus 4 times x minus 4. That's factored. Difference of two squares. A² minus B² factors as a plus b times a minus b. So now we have factored form in the denominator. And with it factored, now we can answer the question, which values of x create 0 in the denominator? I think that's pretty easy to see. If either one of these two terms were 0, meaning that if either one of these were 0, then we would have 0 in the denominator. So that means that if x plus 4 were equal to 0, that would mean x would be equal to -4. And if x minus 4 were equal to 0, that would mean x equals 4. Now, both of these then would be excluded. So what we're saying is the denominator cannot be 0. So that means x cannot equal -4 and, well, I shouldn't say, it wouldn't be at the same time. So, well, I guess, yeah. And x can also not be equal to +4. Both of these are excluded. So here are the excluded values for x. These are not allowed. What would happen if we let x approach 4? Remember from last section, asymptotes? So as x approaches 4, the denominator is approaching 0. As x is approaching 4 or -4, either one of these. If x is approaching them, then the denominator is approaching 0, which means that the quotient, the answer to this division problem, is approaching infinity, either positive infinity or negative infinity. It's going larger and larger and larger, either in the positive or the negative direction. So we're either approaching from the left or from the right. If we're coming in from the left, that would be some value that's very negative, like -10, negative 98765, -5, and then we're approaching between -5 and -4. We're getting close to -4, and this thing is blowing up. It's becoming very, 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 very large, okay? And, or we could approach from the right, you know, either way. 5 approaching down to +4, then that would also go to infinity. How do you know this? Well, let's take a look at the Desmos graphing calculator and just put this expression in there and see what it looks like. I think, you know, you don't have to use the graph in order to answer this question. The excluded values, we've already found them. Here they are, -4 and 4. But in terms of meaning, it's very helpful to look at the graph. When you look at the graph, you begin to understand really what's happening in a much deeper way. So let's look at the graph, because graphs are powerful in giving us understanding as to what's happening. So here we go, off to our graph. Okay, so let's enter this. It's easy. It's 8 divided by x up arrow 2, x squared, minus 16. There we go. Look at this weird graph. Do you see this graph? Is this unusual or what? Look at that graph. Pretty bizarre, isn't it? Wow. An expression that's like just not too complicated. 8 divided by x squared minus 16. Look at this unusual graph that's created. You see anything that's relevant here in terms of the answers that we just had? So you come back over here and you look at this. Sorry, this one. You look at this. We say x cannot be equal to -4, or x cannot equal to 4. And x also cannot be equal to 4. It's an and. We can't have either one. Both are excluded. So take a look at this then. -4 and 4. Where is -4 and where is +4? Take a look at this and, sorry, get this centered up here a little bit. So this is -4 right here, and this is +4 right here. So let's put 2 more graphs up here. Let's put up x equal to 4. Okay. And let's change the way it looks just a little bit. Let's make it a dotted line to make it a little easier to see. And let's do one more, and then let's say x equal to -4. Right here like this. And again, we're going to make it dotted. We can use the blue color as well here, I think. There we go. So here's our graph. Here's our basic graph right here, the red lines. And then you see we have 2 vertical blue lines, which are called what? What's the name of these vertical blue lines? A line to which the graph approaches but never touches. Remember the name? What's it called? Ah, yeah, very good, whoever just raised their hand. This is asymptote. Asymptote, yeah. So we have 2 asymptotes here, one at -4 and one at 4, because these are the values that run the expression to infinity. It becomes undefined because what's the answer to this problem when x equals 4 and -4? It's undefined. It goes so high. So if I zoom out, you find out these lines go forever. They become essentially, well, we can't see them anymore because we're zoomed out so far. They've kind of all merged into one line. Visually, we can't detect the difference here, but actually, they're still going strong. Okay. So now I'm zooming in again, and you see what's happening at these values of -4 and 4. Approaching, but never touching. -4 on the right side again, approaching, but never touching. Asymptotes. So again, the excluded values are the values for which we create an undefined answer, meaning it becomes infinitely large or infinitely small, meaning infinitely positive or infinitely negative, and we cannot define those things, okay? Cannot define them. So here we have it, okay? The excluded values, 4 and -4. Let's move ahead and see if we can find one that's a little more exciting. Let's find something that's slightly more complicated. Let me clear these things out here. So done, delete all. This is cleared out now. I'll go back to our whiteboard for another example. Okay, we'll pick up another example right here. Okay, example number 2, we will be trying to simplify this expression as well as identify the excluded values, and we're going to find the zeros. Find the zeros. So let's say we're going to find zeros. The zeros and excluded values. By excluded values, we mean those values of x that put 0 in the denominator. Those values for x for which the expression becomes undefined. Now, to find the zeros is a little bit perhaps different than maybe we've done before. You need to factor the numerator. Factor the numerator, and then you will be able to see what the zeros are. Remember, 0 divided by anything is 0. What's 0, for example? What is 0 divided by, oh, some crazy number like x squared plus 5y, for example? What's that value? What's 0 divided by x squared plus 5y? We don't know what x is, we don't know what y is, but we do know the numerator is 0. Therefore, 0 divided by whatever in the denominator is still equal to 0. So any way you get 0 in the numerator will create a 0 of this function, okay? Any way you can get 0 in the numerator gives you a 0 of the function. So let's go ahead and factor the numerator. So this will be equal to, I hope you see that in the numerator, the common factor initially that is very obvious is x. So let's factor out x. X times what? X times x squared plus x minus 6, okay? All over the denominator of x minus 1, okay? Now, in the numerator, the second trinomial there, we have two factors. We have x times x squared plus x minus 6. So this trinomial can be factored as well. Factors of 6 are 2 and 3. The difference between 2 and 3 is 1. And notice we have 1x there in the middle. So even though we've done this before, we're going to be doing it a lot more, factoring. So in the numerator then, it's x times x, let's see here. Factors of 6 are 2 and 3, okay? X times x gives x squared, and it's positive 1 in the middle, so this means plus here and minus here. All over x minus 1, okay? All over x minus 1. And this is, of course, still f of x. Our function of x is equal to this thing. Now, in the numerator, there's 3 ways we can get 0. Do you see that? 3 ways we can get 0 in the numerator. Either x is 0, x is 2, or x is negative 3. See? So either this one is 0, x is 0, so 0 times this and this will still be 0, okay? Or this term could be 0, because 0 times this term will still be 0, okay? Or lastly, this term could be 0. And that would mean, in this case, x would have to be negative 3. So if x was negative 3, we would get 0 here in this last factor, times the first 2 factors would be 0. Now, the excluded value is pretty straightforward. If x was equal to 1, then we would have 0 in the denominator, which would blow this thing up and make it undefined. So as far as the zeros are concerned, let's write them down right now. This is the zeros of the function. Will be as follows. We're going to have x equal to 0. Okay, x equal to 2, or lastly, x equal to negative 3. So there's my zeros, and the excluded value is the thing that will give 0 in the denominator. The excluded value will be x equal to 1. Now, I don't think I have to solve these things algebraically, because I would hope that it's pretty obvious. X equal to 1. Why? Because right here, x equal to 1. What's 1 minus 1? 1, right here, 1, subtract 1 gives 0 in the denominator, right? So x equal to 1 is an excluded value. It's the only excluded value in this problem, okay? Now, to bring understanding to this, we've answered the question. So here's the answer to our question. We've answered the question, we found the zeros, and we found the excluded value. But to do a little better, we should look at the graph, just for the fun of it, okay? Let's look at the graph just for the fun of it and see if it brings sense to this whole thing. Because we should be able to see clearly the zeros, right? The graph should cross the x-axis so that y equals 0. We should see the intersections of the graph with the x-axis. In other words, we should find easily the values where y equals 0. Remember, this is y equals, f of x is y, okay? So we should very easily find those values where we have an intersection with the x-axis. The other thing we should be able to see is, where does the function have an asymptote? Where does it shoot off to infinity, either up or down? So we're going to look for the asymptote as well. Where the asymptote is, the equation of the line of the asymptote should be right here, x equal to 1. All right, it should be x equal to 1. So let's find out. So off we go to the graph. And remember our equation, I'm just reminding myself, x cubed plus x squared minus 6x over x minus 1. So that's what we're going to do. So here we go to the graph. So the first thing we do is enter the parent function. We're going to say, instead of f of x, I'm going to say y. Y equals, okay, x cubed, so x up arrow 3 for x cubed, okay, plus x squared, x up arrow 2 for squared. Hey, what did I do? It's not a plus, that was an equal. X cubed plus x squared, okay, minus 6x. And we're going to divide all of that by, I think I'm going to have to put parentheses around this to make it work. Otherwise, it won't come out right. It's all of the top divided by the bottom. So I got to put a parentheses here so there's no confusion. This is the numerator. I'm going to be dividing the numerator by what? By x minus 1. X subtract 1. Whoa, look at this graph. Isn't that crazy? Look at that. Where are the zeros? Okay, here's a 0 right here. Negative 3, 0. Right? So one of those is negative 3. What's this one right here? Another 0, 0, 0. Okay, so 0. And here's another 0, 2 zeros. So negative 3, 0, and 2. How does that line up with what we had? What do we have? Negative 3, 0, and 2, or 0, 2, and negative 3. Okay, there's my zeros. Matches perfectly with our graph. Okay. The second thing now is, where is this asymptote? This one is slightly harder to see, though not too hard to see. This is 2. This would be 1 right here, right? This would be 1. Right here in the middle between the 0 and the 2 is 1. And it looks like the graph is shooting upward and downward around that line. Let's go ahead and create x equal to 1 right here. X equals 1, okay? And just to make it a little more exciting, let's make it a dotted line so that we can see it easier. Okay, like that. And that also distinguishes it from the rest of our graph. So here we go. Let us now zoom out a little bit so we can see it better. Does it look like this graph is approaching 1? Sure does. It's approaching but not touching. How about on the top side? Look at that. This thing goes up. Initially, you might be tempted to think, oh, this is a nice perfect parabola. But it's not. It gets flat on this side as it approaches x equal 1, the asymptote. So back to our other graph, our whiteboard rather. The excluded value, x equal to 1, is also our asymptote. So let's go ahead and write that down here as well. The asymptote is x equal to 1. It's the excluded value. But we write it as an equation, x equals 1. That's the equation of the vertical line that is our asymptote, x equals 1. All right, I think that was a good example. Hopefully that helps you to understand better. Let's move on and pick up another example here. Example number 2, coming right up. Okay, example number 3. We want to find the zeros and the excluded values, just like we did last time around. And let's add to that, since we're finding the excluded value, wouldn't that be another name for the asymptote? Yeah, it would be. So let's find that as well. So here we go. Initially, let's see if we can factor the numerator, because anytime you want to evaluate an expression, it's good to factor it. Perhaps it will simplify down to something that's easier to deal with. So to begin with, let's go ahead and factor that numerator. And so this would become, initially we can factor out the 3. 3 times x squared minus 3 times 6 is 18. And then 3 times 8 is 24. So 8. Okay, so it's reduced down to this now, all over x minus 6. And can we factor that trinomial in the numerator? Will it factor further? So let's put 3 times, looks to me like it will. X times x is x squared. Okay. And then factors of 2 or 8 are 2 and 4. So let's put 2 here. Let's put 4 here. And that's positive 8, so it's got to be plus times plus. A positive times a positive gives a positive, or a negative times a negative. Which is it? Is it positive times positive or negative times negative? Just a quick review here of factoring. Well, you know it's got to be negative times negative because the center term is negative. Where will you get negative 6x if you don't have some negatives in this problem? So it's got to be subtract 2, subtract 4, all over x minus 6. Okay? So what are the zeros of this function now? Zeros will be anything that creates a 0 in the numerator, because if there's a 0 in the numerator, then you know that 0 times anything is 0, and 0 divided by anything is 0. So what gives 0 in the numerator? Nobody's answering? Oh, try again. That's right, x equals 2 and x equals 4. 2 minus 2 is 0, 4 minus 4 is 0. 0 divided by whatever the denominator is still 0. And the excluded value will be that value of x for which the denominator equals 0. Because anything divided by 0 is undefined, meaning it will shoot off to infinity and we can't simplify it. It'll just be undefined. So therefore we exclude that value of x that creates 0 in the denominator, which happens to be, anybody? Yeah, x equals 6 gives 0 in the denominator. So let's go ahead and write down our answers right now. The zeros, first of all. Here are our zeros. X equal to 2. Maybe, in case somebody's struggling, let me just say the zeros would be x minus 2 equals 0, or x equals 2. And x minus 4 equals 0, or x equals 4. So 2 and 4, those are our zeros. And then the excluded value will be Why is my thing's frozen again? Hold on. Here we go. The excluded value you are not right. The excluded value will be that value that creates 0 in the denominator. So it will be x minus 6, x minus 6 equals 0, or x equals 6. That's the excluded value. So I've set it equal to 0 and I've solved. So x equals 6 will create 0. But what we're really saying is x is not equal to 6, because if x is equal to 6, you get 0 in the denominator. It might be better just to say x minus 6 is not equal to 0, therefore x is not equal to 6, okay? It might be a better way to say it. In any event, x is not equal to 6 is the excluded value. Let's jump over to the graph and take a look at this expression right up here. We're going to start with 3x squared minus 18x plus 24. We're going to divide all of that by x minus 6. So off to the graph we go. Okay, I need to clear this out of here. Actually, I'll just change it. 3x squared. So instead of cubed, we'll put a 2, 3x squared plus, what was it? 18x plus 20, or minus 18x plus 24. Okay, so minus 18x, no, x squared, plus 24. All divided by x minus 6. There we go. All right, zeros of the function, 3x squared minus 18x plus 24 over x minus 6. What are the zeros? Well, let's zoom in on this graph and see if we can figure it out. Okay. Bring this up, zoom in a little bit so we can see more clearly. Look at this. There's a 0. See? Remember, a 0 is that value of x that gives the value of the function 0 as an answer. So we want y equal to 0. This is our y-axis, up and down. And right here, that value of y is 0. And right here, the value of y is 0. What's this value of x? 2. What's this value of x? 4. 2 and 4 would be zeros. And then 6, look at this. Look at 6. This graph shoots down, 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 but never touches the blue line, okay? So the blue line is our asymptote. The dashed blue line is our asymptote, and we can see the zeros. Very cool. So does that line up with what we just did? Yeah, does this line up? Does it all make sense? Zeros, 2 and 4, excluded value x equal to 6. So just adding one more little dimension to this whole thing would be to say that the asymptote is what? X equal to 6. That's our asymptote. There we go. Very cool. I think you should have the idea of this by now. I would hope that it's starting to make good sense. There's all the answers to the problem. I trust that that makes good sense to you. X equal to 2, x equal to 4, x equal to 6, and the excluded value, x not equal to 6, okay? So the asymptote is x equal to 6, but the thing we can't use because it blows up is x cannot equal to 6 because it makes it undefined. All right? Very good. Let's move on and see if we can find something else to do. Okay, we're ready to go on with example number 4. What we're looking for here is to simplify the expression and then to find any excluded values. In addition, we'll take a look at the graph and see if we can make some sense out of this. So our function is f of x equals x squared plus 7x minus 18, quantity divided by x minus 2. Now the procedure we follow is exactly what we would do with a simple fraction, such as 12 over 18. And when you look at 12 over 18, how would you go about simplifying that? Well, I know you will probably say, let's see, 6 goes into 12 2 times, 6 goes into 18 3 times, so 2 over 3. And you would be exactly right. But I want you just to watch and see the process to make sure you're clear on this. So we're going to say as follows. We're going to say that this is equal to 6 times 2 divided by 6 times 3. Now notice the factors there. 6 are the same top and bottom. So what can we do? We can cancel them, and then we are left with our simplified result of 2 divided by 3. Simple, right? So what you do, you factor the numerator and the denominator, and you look for any common terms, any common factors, I should say, any common factors that you can cancel, okay? In addition, we want to look for excluded values, which is clearly, there's no variables in this simple fraction, so that doesn't apply. But here we have a trinomial in the top, a second degree trinomial, and then we have x minus 2 in the denominator. So let's see if we can factor this. I think you can all see that x times x gives x squared. And factors of 18, 2 and 9. The difference between 2 and 9 is 7, isn't it? So we can put 2 right here. And we can put 9 right here. And it's positive 7. Therefore, the larger of the two should take the positive sign. So we'll put plus right here, and we'll put minus right here. Now you look at that. We have x minus 2 times x plus 9 all over x minus 2. And of course, you would be right to say that these x minus 2 factors cancel out. But before we cancel it, I want you to notice that we have a variable in the denominator, and the denominator has the potential to be equal to 0. If it is equal to 0, then the function becomes undefined at that point. Okay, it would become undefined. So we ask ourselves the question, okay, what value of x down there in the denominator would cause this thing to be 0? So the answer is pretty straightforward. We say, well, that would be x equal to 2. So notice in the denominator then, we would say x minus 2 cannot be equal to 0, because if it was, it'd be undefined. So that would be x cannot be equal to what number? To 2. That's our excluded value. X cannot be equal to 2. Right? Now let's go ahead and cancel these guys. And we're left with a fraction that looks just like this, or a function that just looks like this. It would be x plus 9. Okay? So f of x equals x plus 9. I really got this other thing here in a bad spot. Let me erase this right now and make it a little more clear. So this is f of x. F of x equals x plus 9. Now, f of x equals x plus 9, that should look strangely familiar. Doesn't that look like a straight line? Y equals mx plus b. M is 1, slope of 1, y-intercept of 9. Okay, y equals mx plus b, you remember this? So, and the m here you see is 1, it's 1x, so it's just slope of 1, and the y-intercept is 9. So this thing should be our graph. Let's go check it out and see. But before we do that, let me write back up here again the excluded value. The excluded value of this particular thing excluded value is x cannot be equal to 2. Now you may wonder, why can x not equal 2? Because the simplified result is right here. This is simplified. F of x equals x plus 9. What does that have to do? Why could x not be equal to 2? And it's because in the original fraction, we had a denominator of x minus 2 in the denominator. So anytime you have a factor in the numerator and in the denominator, which both could be equal to 0, you see in the numerator, if we set x equal to 2, we would have a 0, wouldn't we? 0 times x plus 9 is 0. But it's also in the denominator. Okay, it's actually in both places. And this creates a unique situation. It's called a removable discontinuity. A removable discontinuity. And we'll see that when we look at the graph. So let's switch over to Desmos' graph and have a look. I've already put this thing in here for us. So notice when you graph the top one, okay, when you graph this thing, this is what we started with. It's not simplified. Notice everything's there as our problem originally was. When you graph this guy, you get a straight line. How about that? And then you look at the excluded value. The excluded value was x equal to 2. We said you can't have x equal to 2 because it would create a 0 in the denominator. A 0 in the denominator of the original function. And it is also a factor of the numerator. And again, this creates something known as the removable discontinuity. Let's turn on x equal to 2. Okay, here's x equal to 2. And take a look right here at the intersection point. I better use my mouse. I'm having a hard time here. Okay, let's put in x equal to 2 right here. Notice what happens when x equals 2. It's undefined. Undefined at x equal to 2. Oops, sorry about that. So it's undefined when x equals 2. So right there it is. When x equals 2, we have an undefined value of our function. The value of the function is undefined. Why is that? Because that's where we have division by 0. So effectively, what's happening here, we create a hole. There's a hole right there. You see that circle? That open circle on the graph of the straight line? The graph of the straight line is x plus 9. Notice the y-intercept is 9. That open circle means that is not a point on the graph. Every other place we move on the graph, it's solid. But that open circle is what we call a removable discontinuity. Even though the factor x minus 2 cancels out, it still was in the denominator of our original problem. Therefore, it is excluded. That's why there's an open circle right there at x equal 2. You see that there is no value of y. The value of y is undefined, meaning it blows up. There's a situation there where we can't define what's going on. So, yeah, a removable discontinuity right there. So, simplified answer is x plus 9. That's the simplified answer. The excluded value is the value of x for which the original denominator would be 0, which is x equal to, okay? And we could ask, if you want, we could ask another question. We could say, well, what's the 0 of this function? When does y equal to 0? Well, you could go back over here to our original problem, and you can look at it and you can say, when does x plus 9 equal 0? Well, when x equals negative 9. What's negative 9 plus 9? See, right here. If you put negative 9 right there, negative 9 plus the 9 gives 0, doesn't it? So 0 would be the value of the function when x equals negative 9. So you go back over to the graph and you look down here and you say, is that actually the case? When x equals negative 9, y equals 0. And it's hard to keep it on there. It moves around, but there it is. If it doesn't move, when x is negative 9, y equals 0. It's where the graph crosses the x-axis, isn't it? The graph crosses the x-axis at the 0 of the function. the value of y equals 0 at x equals -9. Okay, well, that is example number 4. Let's move ahead and try another one. Let's do example number 5. In example number 5, we have a little bit of a trick I need to teach you. This is something we have not done so far in, well, maybe we did it once, I can't quite recall, but we certainly haven't done it a lot. There's a little trick for reversing the order of our terms that we are adding or subtracting. Okay, let's take a look. We're going to simplify this. 2x minus 10 over 25 minus x squared. Notice the denominator is the difference of two squares. It's 5 squared minus x squared. But I don't really like the order of that. Let's factor the numerator. Start off by factoring the numerator, and then we'll also factor the denominator. Okay, the numerator can be the following: 2 times x minus 5, correct? 2 times x minus 5. The denominator is the difference of two squares. As I said, it's going to be 5 squared minus x squared, which would factor as 5 plus x times 5 minus x. However, look at the numerator. Instead of 5 minus x, it's x minus 5. It's the same thing, but it's in reversed order. So how do we deal with that? The way we deal with it is we factor out a -1. Watch what would happen if I put a -1 right here, and I then multiply that by, I factor out -1, all right? Factor out -1. And if I do that, then -1 times what equals positive 25? -1 times what gives positive 25? Well, a negative times a negative gives a positive, doesn't it? So if I put minus 25, then when I take -1 times -25, I get positive 25, right? And now I need to have a minus x squared. So if I then put plus x squared, okay, if I put plus x squared, then -1 right here times positive x squared gives minus x squared. Okay, so I've factored out a -1. And by doing so, it flips the signs inside the parentheses. So what we end up with now is the following. We will end up with, and I'm going to move over here now, we're going to end up with f of x equal to 2 times x minus 5 in the numerator, and in the denominator, notice the order now. -25 plus x squared is the same thing as x squared minus 25. So this is a -25 plus x squared, which is the same thing as x squared plus -25. Remember, order of addition, you can add in any order. X squared minus 25 is the same thing as -25 plus x squared. So I can flip it around. And in the end, I have a -1 right here. Okay, I'm putting it in parentheses now, times x squared minus 25. And now I can proceed to factor that difference of two squares. And so it looks like the following. I'm going to have 2 times x minus 5 in the numerator. In the denominator, I'm going to have -1 times x plus 5 times x minus 5. Silly thing keeps messing up on me. There we go. Okay. Notice what we have now. We have an x minus 5 factor in the numerator. We also have it in the denominator. And in the denominator, remember, you can't divide by 0. So what are the possibilities for zeros in the denominator? Well, we have two factors that have a variable there. X plus 5 would be 0. This guy right here would be 0 if x was -5. And this guy right here would be 0 if x was equal to positive 5. So my excluded values are these. Excluded values, and I'll write these here in blue, excluded. The excluded values are going to be the following. X cannot be equal to negative 5, and x not equal to positive 5. Those are the two. X can't be negative 5, and x cannot be equal to positive 5. Either one of these would make these terms over here to be 0. These guys would be 0 if either one of these was true. Okay? So now, I think you recognize that these terms right here would cancel each other out, right? So what is my simplified answer? My simplified answer would be equal to the following. It's going to be equal to 2 divided by minus 1 times x plus 5. Okay? And that can simplify just a little bit more. We can finally end up by saying f of x is equal to, what's 2 divided by negative 1? Okay? What is 2 divided by negative 1? Is it not negative 2? Yes, it's negative 2. And negative 2 over x plus 5, we'll put the minus sign out front. We can do that. So what we're going to do here, we're just going to say that this is going to be minus 2 over x plus 5. Okay. There's my simplified answer. So this is the, if you like, this is the answer to our problem. Negative, or the minus, or the opposite of 2 divided by x plus 5. Okay. Well, graphs. Let's look at the graphs. And let's see what happens when we have this x minus 5 being 0 by putting in 5 for x. In other words, what happens to the function at x equals 5? What happens to the function of x equals negative 5? Remember, when you have 0 in the denominator, something unusual happens. It shoots off. The value of the function shoots off into infinity, and it approaches a line. So do we have an asymptote here? You think so? Any asymptote here? Yes, there is. There is an asymptote. I guess we'll keep it right here. What is our asymptote? Okay, what is our asymptote? The asymptote is the value of x for which the denominator equals 0. The value of x for which the denominator equals 0. Notice that it remains right here. We still have this guy in the denominator right here. So this will be 0 when x equals negative 5. So x equals negative 5 is an asymptote. Okay? Now you may be asking the question, and rightly so, what happened to x minus 5? It got canceled, remember? When you have the same factor in the numerator and the denominator, if x was equal to 5, you would have a 0 in the numerator and a 0 in the denominator. That creates this thing that we just talked about in the last example. It creates a removable discontinuity. So essentially, there's a hole in the graph right there. The graph has a break in it, a hole in it, where x equals 5. Let's verify and see if this actually turns out to be true. So we're going to put in our original problem, which was 2x minus 10 over 25 minus x squared. Okay, so here we are at the graph of this function, f of x or y. equals 2x minus 10 divided by 25 minus x squared. Now we know this simplified down, and we had minus the quantity 2 over x plus 5. Okay, it's simplified down to that. And that creates an inverse variation situation where y varies inversely with x. And we know that when x equals -5, we have an asymptote, an undefined situation where we have 0 in the denominator. And that's going on right here. I don't know if you can see my cursor. If I can find my cursor myself, it would be helpful. And I've lost my cursor. Where's my cursor? Okay, here we are. I found my cursor finally. All right, so notice when x equals -5, right here, you see where I'm at, x equals -5, that's this blue dashed line. It's a vertical asymptote. When x equals -5, we have 0 in the denominator. In case you've forgotten, quickly back to the other graph, notice that when you have x equal -5, then this thing is 0. See, right over here, when x is -5, this whole term becomes 0. Okay, so that creates an asymptote, a vertical asymptote. Okay, so when x equals -5, we have division by 0, which is undefined. When x equals +5, notice x minus 5 is a factor in the numerator and the denominator. So when x equals +5, we have a 0 in the numerator and a 0 in the denominator. This creates what we call a removable discontinuity. A removable discontinuity. There is a hole in the graph. Now, Desmos graphing calculator doesn't show the hole, but when you put your mouse on that point of the graph and you click and you drag along the graph, you will discover that when x becomes equal to +5, we have an undefined value of y. Let's go back to the graph and do this here again. So watch my cursor. I click and now I'm following along. See it following the graph? Here's the red dot following the graph. What happens when I get to 5? That's where the green line is crossing there. By the way, I only put the green line there to show you where x is -5. It is not an asymptote. But what it is a removable discontinuity. Oops. Okay, a removable discontinuity. So here we come, coming along until x equals 5. Right there. X equals 5. What do you notice? It goes from a red dot to a red open circle. We went from the red dot moving along to an open circle. So coming along this way again, watch. Here we go, here we go, here we go, here we go. It's solid all the way until we get right at 5. It's hard to get it right on there. There it is. We have 5, and the red dot went to an open circle. And notice the value of y is undefined. So it's 5, undefined. This is a hole in the graph called a removable discontinuity. Say that, removable discontinuity, a hole in the graph. It's one single value of x for which the function is undefined. And the graph is just like, looks like it's continuous, but at that one tiny little point, there's a hole. Okay, removable discontinuity. So again, the simplified function comes down to this, where we have a vertical asymptote at x equal -5 and a removable discontinuity at x equal to +5. The simplified form of this thing is -2 divided by x plus 5. All right, that ends example number 5, and we're ready to go on to example number 6. Okay, in example number 6, we're doing the same thing. We are simplifying and also finding excluded values. If there's an asymptote, we'd like to indicate that. And so maybe I should go ahead and say that also, indicate the asymptote. Okay, so I've updated this to say simplify, find excluded values, and find asymptotes, if there are any. Okay, there may or there may not be, depending on the problem. So our function is f of x equals 64 minus x squared divided by x squared minus 7x minus 8. Now remember, our process is to factor and then cancel out any common factors, leaving a simplified expression. And then if you have a common factor in the numerator and the denominator that creates a zero in the numerator and the denominator, that is called a removable discontinuity. And any other zero in the denominator is the value of x that creates any other zero in the denominator is in fact our asymptote, okay? And then of course if there's a zero in the numerator, that would be a zero of the function, So let us take a look at this now and see if we can't work through it and make some sense out of it, okay? So let's first off factor the denominator. Let's factor the denominator and see what we get. Okay, factoring the denominator. Hey, this thing keeps moving around on me. Hang on. Okay, factoring the denominator. The numerator is just 64 minus x squared. In the denominator, we have x and x for x squared, factors of 8 with a difference of 1. Well, 1 times 8 is 8, and the difference between 1 and 8 is 7. So that should tell you right there, that's what we're going for. The larger of the outer and the inner terms. Remember FOIL, first, outer, inner, last. The larger of the two should take the negative sign because we have minus 7x in the center of this trinomial. It's negative 7x, so therefore the larger of the two, 8 and 1 should be negative, so we want minus 8x plus 1x. So let's go like this. Let's go plus 1 and minus 8. So notice the outer right here, minus 8x. The inner plus 1x, and the sum of minus 8 and plus 1 is minus 7. So that's how we're going about this. Now, notice we have x minus 8. The numerator in the denominator, we have x minus 8. In the numerator, you see that 64 is 8 squared. So we could write this as equal to 8 squared minus x squared. Yeah, we can do that. But notice that would factor as 8 plus x and 8 minus x. We don't want that. We want it to be reversed. We don't want 8 plus x and 8 minus x. We would like to have x plus 8, x minus 8. Okay? In other words, we would like it to be x squared minus 64 squared. How can we reverse this? How can we get these two guys to change places? Okay? How can we get them to change places? What's the trick? You factor out a negative 1. Factor out a negative 1. So going back here and starting that process, then we could say it's minus 1 in the numerator, minus 1 times x squared minus 64. Now let's verify that this is in fact true. Use the distributive property and multiply. Use the distributive property, multiply this out. Minus 1 times x squared. What's this guy times this guy? It would give minus x squared right up here, right? It would give this, minus x squared. Okay? That's what it would create. But we don't want that. Sorry, I don't want to keep my blue marks on here. It would create minus x squared. And what is minus 1 again? What is this guy? Minus 1 times negative 64. Minus 1 times minus 64 is positive 64, and notice this was positive 64. So factoring out -1 flips the order. It turns the two things around, which is kind of cool. You know, when you're subtracting, you can reverse the order of the subtraction by factoring out -1. Remember that trick, okay? It is a little trick, you know, if you haven't seen it before, it's a little surprising probably the first time, but it works beautifully. So we have -1 times x squared minus 64. In the denominator, we still have x plus 1 x plus 1 times x minus 8. Now let's go ahead and factor that numerator. See what we get. The numerator is -1 times x squared minus 8 squared. It's going to be x plus 8 times x minus 8. Remember, I probably should have shown this, but in the interest of time, I didn't. But notice that x squared minus 64 is equal to x squared minus 8 squared, which factors as x plus 8 times x minus 8, okay? So this is just a little explanation right over here. Take note of this. The numerator is the difference of two squares, okay? The denominator is as it was, x plus 1 times x minus 8. Do we have a common factor in the numerator and the denominator? Yep, we sure do. And if x was equal to 8, see these two guys? They cancel. But if x was equal to 8, we would have a 0 in the numerator and a 0 in the denominator. So what happens when x equals 8? On our graph, we should have, what should we have? Anybody? We should have a hole. What is the name of that hole? What do we call a hole in the graph when you have the same factor in the numerator and the denominator, and a value of the variable there creates a 0, or it creates that factor to become 0. That hole is called anybody? Removable discontinuity. Removable discontinuity. So we should find that. So let's now write our simplified form. Our final answer, which is simplified, is going to be as follows. F of x is equal to, and we can put that minus sign out front now. We can write it as minus x plus 8. Just hold on a second. I don't know why it is, but this stylus, I have to keep putting water on it. If I put water on it, then it works. If I don't put water on it, it just doesn't seem to get the thing to write. So I have to keep dampening it, sorry. So minus x plus 8, and in the denominator then, x plus 1. There's our simplified answer. This is the simplification, okay? That's our simplification of the whole thing. It works out to be x plus 8 over x plus 1 with a minus sign out front. Okay, now let's take a look at the graph. The graph should reveal some pretty interesting things. Okay, here's our graph, 64 minus x squared, all divided by x squared minus 7x minus 8. And recall, we said that x cannot be equal to, go back over here to our whiteboard again, x cannot be equal to -1 or equal to 8, okay? I guess I didn't actually write those down yet, I should. What are the excluded values? Okay, excluded values. Excluded values would be x not equal to 1, or sorry, x not equal to -1, and x not equal to 8. Those are the excluded values, and we would have an asymptote at x equal to -1. Remember, the x minus 8 cancels, right? So that's going to be our removable discontinuity, x equal to 8. But the other one, this guy, remains. Even in our final answer, you see it remains. So this one, in our simplified version, still has a 0 at -1. So this is, in fact, an asymptote, okay? If, after simplification, you still have a variable in the denominator, then that variable is an asymptote. It will create an asymptote. Okay, so let's go back here to our graph and see what we can do. Okay, back to our graph. So here's our graph. Do we in fact have an asymptote at x equal to -1? According to what we had been saying, it should have an asymptote, but x equal -1. So what if we zoom in on this and study it a little bit? Here's -1. This is 2 marks over. There's -1. We go down. Does it look like it's approaching to -1? Does it approach this line? Again, if I zoom in a little bit. So -1 is right here in the middle where my cursor is. Is it approaching that line? Well, it's a little hard to see. So let me make a suggestion. When it's hard to see, go ahead and enter it on your graph. Let's put x equal -1 right here. X equal -1. Okay? And to make it more legible, let's go ahead and make that to be a dotted line like this, maybe like this. Okay, see -1? Now we can visualize it if we zoom out. That's x equal -1, or zoom in rather. So as we zoom in, is it in fact approaching that line? Does it look like an asymptote to you? Is the red line getting closer and closer to the blue dashed line? See that? That blue dashed line is in fact an asymptote. Yes, it is. It worked out perfectly. You can see that very nicely now. That's an asymptote. And the same thing above. If you follow this graph upward, the higher you go, you'll notice that the red line is approaching the blue line, but it never touches. It just gets closer and closer and closer. You keep subdividing the distance between the two, and you can keep subdividing forever, in theory, okay, in theory. In practice or for practical purposes, it comes to that line, but in theory never touches. Okay, so that is our vertical asymptote, x equal -1. Now there was another value. It's the hole in the graph, remember? It was that hole in the graph. So if you look back over here, once again, you look back over here and notice this x minus 8 was in the numerator right here, and it was also in the denominator. It was here and it was here. If x equals 8, we have a special situation where we have a 0 in the denominator and the numerator. Both of them would be 0. When you have a 0 in the numerator and the denominator caused by the same factor, then that creates a hole in the graph. A hole in the graph, what's it called now? We've done this several times. I've mentioned it again and again. The hole in the graph is called, I bet Mrs. Dunder could even answer me, a removable discontinuity. Let's go back to the graph and see if x equal to 8, x equal to 8. See over here, this is the excluded value, x equal to 8, or x not equal to 8, but I'm saying when x equals 8, we have this hole in the graph. That's why it's excluded. We don't want the hole in the graph, so we exclude it. It's not allowed. So when you look at that point, you'll see that it's undefined. Back to the graph, let's see what we have. Okay, zooming out so we can see things again. Okay, so we zoom out, and then we look for x equal to 8. If you want, why don't we go ahead and say x equals 8 over here, just so that we can see it. We can identify the point easily, all right? It helps us to know where is 8 on the x-axis. Let's go ahead and make this guy to be a dashed line. Okay, we'll make it to be a dashed line so that it's, again, easier to see, okay? So now zooming in on this a little bit, zooming in, what happens when x equals 8? We have a removable discontinuity, a hole in the graph, a hole in the graph. So we come along with our cursor, and we click on our line, and we begin to drag it. And we drag that guy along. Here we go. I don't know quite how to get the point to stay, but now it's staying. Here we go. When we come along, we're at, where are we at right now? We're at 6.9, 6.93. There's 7. Now we go on until we get to 8. When we get to 8, we should find something funny. There it is. Believe it or not, 8 and undefined, a hole in the graph. Notice the red dot went to an open circle. It's a hole in the graph. That's why it's labeled as undefined. And this point 8, this point 8 is called a removable discontinuity. And I should probably write that down over here so that you can see it written. It'll help you to remember it. So our final step is to identify the asymptotes. We'll begin with the vertical asymptote. What is the value of x that creates 0 in the denominator? This will be the vertical asymptote. So looking at our problem here, we see that x plus 1 is in the denominator. And if x is equal to -1, then we know that the denominator will become 0. So our vertical asymptote is x equal -1. How about the horizontal asymptote? How about this one? This one's a little bit easy, or a little bit harder to see. When you look at the equation x plus 8 over x plus 1, stop and consider where the value of this quotient goes as x becomes larger and larger and larger. So when you look at the graph over here, notice that if you run out to the right or to the left, either direction, the farther you go, you see that the graph is approaching this green line. So what is the value of y anywhere along this green line? That's the question. So you look at f of x and you analyze it based on larger and larger values of x. So just think for a minute, what if x was 1,000,000 and then you add 8? Is 1,000,000 and 8 very different than 1,000,000? Not that much different, though it is different. And how about in the denominator, 1,000,000 plus 1? 1,000,001 versus 1,000,000. So let's just take 1,000,000 and think about it. 1,000,008 over 1,000,001. Do you think the answer is very different than 1,000,000 over 1,000,000? How about 10,000,000 or 100,000,000? As you get bigger and bigger and bigger, adding 8 or adding 1 to such a large number doesn't really change its magnitude percentage-wise that much. It's a very, very small part of such a big number. So as you let x become larger and larger, this ratio really starts to look more like x over x. because the 8 and the 1 don't change things very much. Essentially, it's just x over x. What is x divided by x? X divided by x would be equal to 1, wouldn't it? So essentially, this thing starts to look more like, as x becomes very big, it begins to look more like minus x divided by x, which is just equal to minus 1. So in the limit, as you let this thing go bigger and bigger, this thing begins to look like y, we're dealing with f of x, it begins to look like y equals negative 1. Okay? So this thing would be what it is if x becomes very big. It begins to look just like x over x or negative 1. Y equals negative 1. So if you go back to the graph and you look at it for a little bit, notice that that is in fact what happens. It begins to settle down to y equals negative 1. Negative 1, 2, 3, 4, 5. Yes, this is negative 1. Y equals negative 1 is our horizontal asymptote. Well, folks, this has been a bit of a long lecture, but I hope it brings really a deep level of clarity to what's going on. Please listen to this lecture a couple of times and take notes, write down things so that you won't have to spend so much time reviewing. I'm going to give you another little quiz like we did last time. I think doing the little quiz maybe is easier than doing homework per se, and perhaps it kind of encourages you to watch the video and study a bit rather than just try to get some problems done. And we're going to have to stop. Isn't that sad? End of the school year. Don't cheer. You should be really sad. Come on, guys. This is good stuff. You have been learning math and you are ready for Algebra 2. Can I tell you, you are ready for Algebra 2. If you've survived this and you're holding on strong, guess what? You are ready for Algebra 2. In fact, you're very ready for Algebra 2. You will be able to do really well, I trust. So, of course, if you're cheating, if you're copying homework and whatever, just trying to skate through right now, you're hurting yourself. Don't do that. Study. Yeah, really study. And listen to this lecture a few times and you'll be good. You'll be doing really well. Okay, well, if you have questions, don't hesitate to text me. I would suggest you call me on WhatsApp because sometimes the little text message sound is so faint and I'm going around campus doing other things I have to do. Sometimes I miss it. I don't hear it. But if you call, it's much more likely that I'll hear the cell phone going off. So if you need help, give me a call. All right, guys. Well, it's been good. I've enjoyed doing this today. It's been fun. It's taken me a while, but I hope that you will enjoy it as much as I have enjoyed making it. All right. Bye until next time.